It's a hard act to follow.
It's a hard act to follow. Good morning, everyone. Welcome to this morning's session, the last morning of the workshop. Even though we're a little empty, we're going to get going because our speaker has a plane to catch. And our speaker is Tom Mason from UCLA, and he's going to speak about microrheology. I think I'm in terms of
Okay, is this okay? Can people hear me fine?
Oh, it
sounds like it.
Yeah, you're good.
Okay. All right, well, thanks. And I wanted to thank Yvonne and Noel for inviting me here, and I've had a great time. It's really been nice. And I also wanted to thank ICAM and I2CAM for their sponsorship of this workshop. This is really great. And just like the microrheology workshop we had at UCLA back in February, it's really nice to be able to bring in international and as well as domestic people in having and building science around complex adaptive matter. So this is really cool. So, all right, I'm going to start off here this morning with a review of microrheology and explain what this is, and hopefully move in from there into some of the applications and developments in the field of microrheology, and then tell you about some of the things going on in our lab related to this, and then maybe open it up for questions, discussion about applications in the area of liquid crystals and anisotropic soft matter in general. And so the work that I'm going to tell you about today, the work on nonlinear rheology was done by my grad student Jim Wilkie, who's going to Harvard to work with Dave Waits and Michael Brenner. And Zhendong Cheng did a lot of the work with the microdisks that you'll hear about. And Daphne Weiss was a postdoc at UCLA who did work on biomicrorheology and went to Technion afterwards. So what is microrheology? Well, rheology is the study of flow and deformation of materials. And so microrheology is the study of that flow and deformation at microscopic scales. Basically, we like to look at local properties of the mechanical response of materials. And so that's basically what it's about. Sometimes you might have materials that are hard to synthesize, and you might only have a very small volume of those materials too, and you might want to know the mechanical properties. Then microrheology might be a way of actually determining that as well. People in the active adaptive materials community are interested in understanding what's happening to the mechanical response inside cells in living systems, right? So if you have cells that are 10 to 100 microns across, and then you want to know what the rheology, the mechanical response is here versus there, then maybe you can figure that out and map out locally different rheological properties and dynamically changing media where there's actually not only thermal driving that's going on, but you have active motion of molecular motors and other kinds of structures in the cells. So basically just taking a piece of chicken and loading it into a rheometer might tell you some things about the material, but you're going to have some problems actually trying to deduce the source of what biological components are actually giving rise to that elasticity or viscosity. And so, it would be nice to have methods that can go down to a small scale. So this is just a brief primer on rheology. Many of you know this, but I'll go through it quickly. But basically, the kind of mentality I'm approaching this with is thinking about isotropic materials right now. I'm not thinking about highly anisotropic materials for the moment. And if you want to characterize mechanical properties of an isotropic material, one of the simplest ways to do it is just with mechanical rheometry. So you can take that material loaded in between two solid plates. You have that soft material. In this case, it's a cone and a plate. And basically apply a strain with a motor to the lower plate and then measure a torque on the upper cone. And then that torque is going to basically tell you, it's a function of frequency, the either relative ratio of energy storage and loss in the material, so if you would, like a mechanical susceptibility. And You can have different geometries for doing this. Cone and plate, double wall clouette. This has more surface area, so for weaker materials, this is typically used. And basically, the idea, in those systems, typically you're working with, milliliters, many, up to 10 milliliters, 1 to 10 milliliters of volume roughly, and that's a lot for some exotic materials that you'd like to know the properties of. So it'd be nice to have a way of doing that for lower volumes. So I'm going to be talking a lot about linear viscoelasticity of materials, and I just wanted to go over that very briefly here. So if you have, this is the traditional way of doing the rheology. You put a material between two plates, you move one plate relative to another plate, so you apply a sinusoidal strain, which is just the amplitude divided by the gap, that maximum, and then you measure the stress on the other plate, and that lags the strain, and you get some time lag delta t, which you can turn into a phase lag by multiplying it with a frequency. So you get out the measured stress from that sine wave, and then you can break that down to an in-phase and out-of-phase part. And the in-phase part is the storage modulus, reflects elastic energy storage in the material, related to microscale and nanoscale structures that store energy. The loss modulus is basically dissipative, and you can basically you can express this also in terms of a complex viscosity. It's completely equivalent, just a different form of expression, and basically the storage modulus is just I omega times the complex viscosity. So when the stress is perfectly in phase with the strain, then the storage modulus is large, and when it's 90 degrees out of phase, the loss modulus dominates. So I want to introduce this in terms of photonic rheology. So people have been doing photonic rheology for quite some time. If you think about just simple viscosity measurements and looking at diffusion of particles in a microscope, if you have particles, microscale particles dispersed in a viscous liquid and watch them diffuse, and you know Stokes-Einstein relation, then you can extract the viscosity out of that, which are using photons to actually do that. People also do particle sizing through scattering methods like dynamic light scattering, and that's been done for a long time. In a sense, if you know the probe size, then you get out the rheological properties of the material, like the viscosity. But then the question is, well, how do you generalize that to a system in which viscosity isn't the only mechanism of resistance of motion of the sphere to thermally excited motion? So the basic idea here is to take the small-scale dynamics of probes that are embedded into the material. And these probes hopefully have a nice geometry, so the flow problems that people solve with fluid mechanics might be usable to actually determine quantitative information. So you might be able to measure something like a mean square displacement of particles through either dynamic light scattering or particle tracking, real space methods. And then from that, around the particle, you might be able to interpret a local mechanical response. So you might have some frequency-dependent friction function that might be complex. And then if you make further approximations and interpretations, you may be able to get out the large-scale bulk mechanical response of the material if it's not heterogeneous. And so in that movie, you were basically seeing the translational and rotational diffusion of a wax microdisk in water. And so basically, we're hoping to use thermal excitations to drive motion of particles and then deduce from that linear viscoelastic properties. With thermal excitations, you're never going to get out of the linear regime. Basically, you'll be in the linear regime. To get out of that, then you have to do a different form of microrheology, which involves active driving. And so just a preview of what I'll be telling you about is, here you have a mean square displacement measured as a function of time, and in a complex material like an emulsion that's elastic, at early times you have diffusive motion of probes. Later times, the probes feel the elasticity of the medium around them, and they can't move out of a certain region or area, right? And so that's reflected in this bend and turnover in the mean square displacement. And what we want to do is take that function that mean square displacement as a function of time and convert it into mechanical properties as a function of frequency. So how do we do that? So this is just a bit of history. I was working with Dave Waits at Exxon. I was a grad student at Princeton, and I was working on rheology of hard sphere dispersions and emulsions, dispersions of monodispersed deformable spheres. And basically, I was measuring a lot of properties using the mechanical rheometer. And we were also using a technique that Dave Waits, Dave Pine, Paul Chaikin, and Eric Herbolzheimer developed called diffusing wave spectroscopy. And from that, we were getting mean square displacements of probe particles in viscoelastic materials. So we were getting mean square displacements that weren't just purely diffusive. And so the question was, well, how do you relate these two properties that we're measuring, or can you do that in a systematic way? And so that basically was the inspiration that gave rise to this approach of thermal diffusion microrheology, or people sometimes call this passive microrheology. That's another term that's used in the community. And basically the idea of that is that you're essentially letting thermal energy be the driving stress, and it's driving stress that's fluctuating at all frequencies. So you have basically a broadband frequency probe through those thermal fluctuations, and then you measure the strain through the mean square displacement. So you can do that with scattering or real space. And the nice things about it are, well, you don't have to have external driving. You know you're getting linear properties out because you're looking at thermal excitations. It's over a very wide frequency range. There are other methods called active microrheology methods. And actually the field started with this, okay? So Seifritz and Heilbronn and other people in the 1920s actually put magnetic beads in cells and began moving these magnetic beads in the cells and trying to probe rheology in cells back in that time. So it's quite old, it's many decades old. There was a revival in this in the 90s, people looking at actin networks and inside of cells with magnetic beads. And then optical methods with laser tweezers were developed to move particles, dielectric particles around, and you would watch the motion, and you could basically do a very small-scale version of that mechanical problem that I explained earlier with forced excitation. But I'm going to focus on thermal diffusion mostly, just recognizing that other method is out there and it has been around for quite some time. Basically, for simple diffusion in a viscous liquid, we have a diffusion coefficient. The mean square displacement grows linearly with time. We know the Stokes-Einstein relationship, which relates the diffusion coefficient to viscosity if we know the probe size and we know our temperature. So basically, we can use that pictorially here and generalize that. If you imagine a sphere in a viscoelastic material, so I have this spaghetti drawn outside of the sphere that basically represents something like a polymer solution. Could be other materials, but basically the problem is to look at the motion of the sphere in a viscoelastic complex fluid. And so from this, say, mean square displacement that could go be diffusive and then subdiffusive, having a log slope less than 1, and then back to diffusive again. This relaxation might be related to the disentanglement of the chains thermally over time, right? That long time relaxation. This viscosity down here might be related to the solvent in this plateau, solvent viscosity, and then this plateau would reflect the elasticity of the material. So we have this mean square displacement as a function of time, which if it's linear, we can just extract a diffusion coefficient, get a viscosity, but in general it's not linear, so how do we get these complex properties out? So before I do that, I'm not going to go through the derivation in extensive detail, but basically we're going to treat the material around the probe as a continuum. That kind of approximation is very important for this. If you have a highly heterogeneous material, then that approximation may not be very good, and you might not be able to get a bulk elasticity and viscosity out of that. So a good way of trying to maintain that is to ensure that the particle size is much greater than, say, the characteristic mesh size or entanglement length in the network. And so, you know, in a lot of the polymer solution examples that I'll show you, that's definitely the case. We assume state boundary conditions. With different surface treatments of the particles, you can get different kinds of boundary conditions. And so a lot of the time we actually want the particle bound to the network, not with some kind of shell or corona of just, you know, solvent around it without it being actually in the network. Basically, there's a problem in terms of knowing the flow field of a complex fluid outside of even a spherical particle, where that problem has been solved for a viscous liquid. But then if you have a viscoelastic liquid and you're trying to deduce the viscoelasticity, but you don't know it in advance, that can be a difficulty. So we make a simplifying assumption of just the Stokes flow around the probe sphere is fine. And so for materials that are in liquids, typically this is not such a bad idea. So if you have dispersions in liquids or polymer solutions, that tends to work pretty well. So the equations of motion, you have a thermal driving term. You've got a memory function which describes the viscoelastic response. And that memory function here is like the equivalent of the Stokes drag. It includes the geometry aspects of that problem, the boundary conditions, and in it is also the frequency-dependent viscosity, this eta. And so we can relate that to the modulus, and solving this using energy equipartition and the fluctuation dissipation theorem, we can basically get that the frequency-dependent modulus, so this is a Laplace frequency here, is inversely proportional to the Laplace transform of the mean square displacement. And so you can see we've got an energy density here, thermal energy over the radius of the particle times the mean square displacement. And this is neglecting inertia. If you get up above about 10 to the 6 hertz or so, then you have to start worrying about the inertial term, and we can correct for that. But this is good over a very wide frequency range. And it's been used for a lot of materials at this point, and quite successfully. I'll show one example here where we've done particle tracking microrheology. So the original experiments, as I mentioned before, were with diffusing wave spectroscopy using light scattering, multiple light scattering technique to measure the mean square displacement. You can also use particle tracking. So when I was at Johns Hopkins, I hooked up with Scott Coe, who worked in Mike Sheets' lab, and those folks were doing motion of molecular motors. And so they were doing kinesin work and basically using a quadrant photodiode detection, and the laser beam would be deflected by the motion of the probe sphere that was tethered to the motor, and then they could measure the stepping motion of the motor itself with that very sensitively. And I thought this would be a great idea to use for, a great method to use for microrheology. So we used that, essentially that quadrant photodiode setup in order to deflect a laser beam of a probe embedded in a polyethylene oxide solution and measure the trajectory in 2 dimensions. And then from that we can calculate the mean square displacement. And so we have the diffusing wave spectroscopy result, which you can see is going over 7 orders of magnitude in time here. And then we have, the laser deflection particle tracking results right here. There was some vibration of the table, so that's what this ringing is, but basically it's a nice curve. We can calculate from that the mean square, from the mean square displacement, we can calculate the frequency-dependent modulus and overlay the results, and the diamonds are the mechanical rheology. And so, we find fairly good agreement for this polymer solution using a variety of different optical techniques and over a fairly wide range of frequencies here as well. And so it turns out that these optical methods are really nice for soft materials, and it's kind of a sweet spot for them in terms of the elasticities. if you get the elasticity being really high, many orders of magnitude higher up here, 10 to the 6, say, dynes per centimeter square, then, it's sometimes quite difficult to see the motions of these microscale probes. You might have to reduce the probe size or try to devise other methods. So these have been, this approach has been validated for a lot of systems: polymer solutions, worm-like micelles, hard sphere dispersions, emulsions and nano-emulsions now, clays. Now, it can't be, the attractive systems of particles are sometimes problematic because they're heterogeneous in structure, but if you have homogeneous glasses of repulsive objects, then it tends to work well. Micellar solutions. This is an example for an emulsion, basically, where the droplets themselves are being used as the probes in a diffusing wave spectroscopy experiment, where there's a high density of a high volume fraction of these droplets. In some measurements, you will only want a very small number, a very dilute volume fraction of probes. And different techniques, optical techniques that have been used, diffusing wave spectroscopy, simple dynamic light scattering, laser deflection particle tracking, and video particle tracking. There have been more developments since the simple version of this. One is two-point and two-particle microrheology, so examining local rheology between neighboring probe particles that are near one another, or you might have a material in between them, and you want to probe the viscoelastic response of the material in between the two spheres. And so you can measure the positions of the spheres by video particle tracking. In the example that I did here with DNA in this work, a DNA solution, basically that was, there were fluorescent microparticles that were moving, and we were using averaging methods to get the centroid of the intensity, and then use that to actually determine the trajectories. And so, one of the first example of this was just to simply eliminate convective drift. And I would have to say that as a tutorial, that's one of the major problems for people trying to do microrheology, actually, is making the sample cells, sealing them without air bubbles and other kinds of problems in there, and eliminating the convection. Because obviously, if you have convection, you can't use the equations very well that are based off of fluctuation, dissipation, and thermal equilibrium. But if these two spheres are convecting in an overall drift, then you can difference their trajectories and basically calculate mean square displacement that gives you a much, a reasonably accurate measure of the viscoelasticity. And this experimental approach was taken a lot further by John Crocker and Alex Levine, and Tom Lubensky worked on the theory. So John was in Dave's lab, Dave Waits' lab. And so they developed a very nice two-point tensorial analysis of the two-particle microrheology experiment. So they call that two-point, and this is two particles. So I guess the experiment was done first, and then they developed the theory and the formalism for looking at motions of the two spheres where they're coming together like this versus going transverse or side to side. And so there are different types of rheological information you can extract from these different parallel and perpendicular mean square displacements. And so that's something I'm not going to dwell on a lot, but basically this can, by varying the separation between the probes, it can provide Q-dependent or spatially dependent measure of the viscoelastic response. And it also is better with heterogeneous materials. Basically, if you have heterogeneities or coronas around particles that have different mechanical properties, then this type of approach can actually help in that regard. So it's definitely a nice development that's happened. There are a lot of advances in this area. We were here at two-point microrheology, and people have been looking in living cells. There are problems there, obviously, because you can't apply fluctuation dissipation of just thermal fluctuations in a living cell, but we're trying to, a lot of research groups around the world are working on microrheology in living cells. In fact, I just came from the International Congress of Rheology, which is in Monterey this year, basically made the plane trip from there directly to here. They have about 4 or 5 sessions on microrheology of various kinds, And a lot of them are focusing on this area of biomicrorheology, living cells, to try to understand how to interpret those non-thermal fluctuations of probe particles. And so, you can have energy equipartition, you can have translational modes of diffusion, you can also have rotational modes of diffusion. And so we've done work on rotational microrheology, and Dave Waits and Margaret Gardell have used other probes. They've used just microtubules or other types of structures in cells as probes rather than just spheres. And they have speckled microrheology, and people are, I only mention this in our group, but there are many groups working on forced rotations of particles in media of one kind or another. And this is just a reminder that the field is growing. We had about 120 people come to our microrheology workshop at UCLA earlier this year. And so that was a lot of fun, and that was also an ICAM sponsored event. Here are some of the frontiers that we talked about briefly there, there are issues of dimensionality. For instance, doing interfacial microrheology on a 2D surface. There are issues with heterogeneity of materials, like in materials where there are attractive interactions between the constituents, those microscale and nanoscale constituents. That can create those attractive interactions can create heterogeneities that might make it difficult to apply the microrheology formalism that I was talking about before. You can have an anisotropic media. I think that would be very interesting, folks in this audience. Basically, how can you potentially use this for this general approach and expand it and make it rigorous for anisotropic materials of various kinds? Might have defect structures and other things like that in it. I think about all those different elastic constants in Landau-Lifshitz. My mind starts to get a little bit blurry when I begin to think, because we're just dealing with isotropic materials here, and there's already a considerable amount of complexity there. Probe size and shape. So spheres are great, but there are other shapes out there now. So what are they doing? You can have different boundary conditions. Multi-probe techniques like the two-particle or multi-particle. You can go and drive the system into nonlinear response. Look at the active media, not just thermal media, So this was an image of a word that my student Jim Wilking wrote with our lithographic particles using laser tweezers to drag them around. Let's see if I can replay this. This one right here is a movie of is it going to play? It's not. Okay, well, do it this way then. Let's see if I can activate it again. Okay, so basically these were letters that we made lithographically, diffusing in water. They're near a slide surface, so that's why they're not orienting in all different directions. But the idea was that there was an exhibit at the Museum of Modern Art that we participated in, and you write this word mind, and then as it diffuses away, you lose your mind. So, that's basically what we had there. Thermal diffusion helping us to, entropy helping us to lose our mind. And this was basically a disc in gelatin where you apply circularly polarized laser tweezers to exert a torque on the disc. And this one is a disc in water with circularly polarized laser tweezers showing this beautiful light streak that Zhendong Chen did. So I'll get to that later. So let's go on to some non-spherical probes. So let's talk about aqueous dispersions of waxed microdisks. So this has fascinated me. I work on emulsions a lot. I'm into the materials, not just into techniques. And, this was interesting. I mean, people have seen tactoids in liquid crystal community for a long time. And I don't think this is maybe anything such big news to the liquid crystal community. But, we had a simple wax that had a melting point just above room temperature. We emulsified it into an SDS solution. And cooled, so when it was hot, we emulsified it, then we cooled it down. And so basically these spherical droplets, just decided to change their shape based on the energy, the bulk energy between planes of the molecules. And I find this very interesting because basically the interfacial tension is strong enough to, in the plane of the molecules, if you imagine layers of planes of molecules, and in the plane the molecules can be moved around by the interfacial tension, so that's why you get a circular perimeter. But it can't overcome the between plane kind of interaction, so you still have flat planes. And I suppose there are Wolf constructions and other kinds of things that people have looked at for a long time to explain the aspect ratios and whatnot, anisotropic surface tensions and so forth. But the point is that we have a way of making very nice molecularly flat disks that are microscale using this simple method. We can make a lot of them. And there are a lot of things I don't understand about the kinetics of this process, actually. So I'm not going to dwell on the kinetics of the shape change from a sphere to a disk. But that's a fascinating area in itself. But anyway, we basically have a birefringent disk that we can play games with using polarized laser tweezers. And you've seen this movie of the disk diffusing around. So basically we can look at either translational or rotational motion. Spheres are hard to look at rotations, obviously, unless you somehow mark the sphere in some way or make it of an anisotropic material itself. So we can go through, and the same idea I told you about before, we can do that for Stokes-Einstein, the bi-rotational diffusion. And so we can basically measure mean squared rotational displacements or mean squared angular displacements as a function of time rather than just the translational mean squared displacement. Relate that to a rotational diffusion coefficient and then using Stokes drag again for the rotation. And so you can go through the whole formalism all over again and extract the modulus. And you can do that by taking the Laplace transform of the time-dependent mean squared angular displacement in this case. So that provides a connection, a formal connection between the mean squared angular displacement and the linear viscoelasticity of the medium locally outside of that. And I should mention that in the world of rheology, there are many equivalent representations of linear response, and they go under different names. You have things like the creep compliance, which is this J of T. You have the frequency-dependent storage and loss moduli, or complex modulus. You have frequency-dependent viscosity. You have a stress relaxation modulus. These are all it's all terminology for the same response function, the same time-dependent linear response function. It can be just expressed either in the time domain or frequency domain, and you can call it different things depending on whether you're thinking about a stress response or a strain response. So this one is basically this creep compliance is basically the response to a step stress. So you would step the stress up to a certain level in the material, then watch the strain as a function of time, and then you would take that strain as a function of time and divide it by the stress, and that would give you the creep compliance. So anyways, you can simply just take the mean squared angular displacement and directly relate that to the creep compliance. It's all equivalent. So in this, basically what I'll do in the next few slides will lead up to the rotational diffusion microrheology. We can take these wax microdisks, trap them in a laser tweezer, and if it's linearly polarized, we align the disk in a harmonic potential. So we can control the strength of the potential by tuning up the laser power. And also we get this light streak that comes out, and that's a natural optical lever. So that people who work with angular deflections love optical levers. So we have an optical lever that's based off of a microscale particle like that in the trap itself. So we can use that to measure the angular displacements very sensitively. And so that's nice to have that light streak. It's kind of like a cylindrical lens, functioning as a cylindrical lens. And at the time, there were some theories and predictions that disk-like particles wouldn't trap in laser beams, but this disk happens to have a thickness that's comparable to the beam waist of the focus spot. So, this one does trap, and it's kind of, if you imagine a sphere outside, it's not too hard to believe that that actually would trap. So at what aspect ratio a right circular cylinder goes from trapping on edge like this to trapping along the long direction, along, you know, where the rod would be aligned along this way. I don't know that anyone knows that aspect ratio exactly at this point, but I'd be curious. It's probably NA dependent on other things. So anyway, we take this, we can align a disc. The point is we can align a disc and we can measure angles. And so you can look at the fluctuations of the disc. These are thermal fluctuations of the disc in this trap. And you can think of the trap as maybe representing an elasticity of a medium outside. At least we haven't put it in a medium other than water yet, but we have a way of creating a restoring torque. And so moving on, I think. Okay. Computer is a little... Okay, so here we go. All right. Mean squared angular is, so here's the time series right here in the inset. So that's what we measure, those rotational fluctuations. And basically we can take the mean squared angular displacement of that. We get a diffusive behavior at early times, and then we get this turnover to a saturation here, and that's reflecting the strength of the harmonic well in the trap that we have. And so this was measured using a fast camera. So this was an application of fast CCD cameras to the tracking. That was a new thing at the time. So basically we can solve the equation of motion for the mean squared angular displacement, and we basically find a form that is common for a harmonically bound Brownian particle. So we think this is the first demonstration of that in a rotational sense that's so clear. So we can take that and fit our data to that formula. And the fit is pretty nice, and basically we get within a factor of 2 of the quantitative value of the angular diffusion coefficient that would be predicted using an ellipsoid of the same aspect ratio as the disc that we have. So our discs are typically about a micron thick and maybe a couple of microns in 3 microns in diameter. Here we vary the power of the laser, and as we increase the power, the saturation level goes down, meaning we're confining the disc more strongly in the trap. And so for rotational diffusion microrheology, what we do is we take the disc, put it in a viscoelastic material, and then we apply high enough laser power that we line it up so that we can use the light streak tracking method that we developed. So we line it up with higher laser power, wait, then we apply lower laser power and just use the light as a probe. So we're not trying to apply torques to it anymore. We're just using the laser light as a probe of the thermal fluctuations after that point. And so basically we're looking at the rotational fluctuations, and this is an example of what we see. Here are the rotational fluctuations, the time series. So this is a particle, this is a wax microdisc in a 4% solution of PO, 900,000 molecular weight in water. We have the fast camera, and basically these polymer entanglements are leading to an elasticity in the system that you wouldn't have if it was just in a viscous liquid. And so what we can do is take the time series, calculate the mean squared angular displacement as a function of time. We see subdiffusive motion here at our shortest times, indicative of a higher frequency elasticity reflecting the entanglements of the PEO solution, and then a low frequency of relaxation out here at longer times. And we did this at 2 different frame rates, so those are the 2 different curves, and we get reasonably good agreement with the measured mechanical modulus of the PEO solution. There is a slight difference here, and I have to tell you that because the rotational form of microrheology, the storage modulus is inversely proportional to the cube of the radius of your probe particle. You need to know that radius pretty well because it's cubed in that formula. So if you're measuring an individual probe like we do microscopically, when you have a relatively large uncertainty due to the, well, where exactly in that pattern of light and dark is the edge of the particle, so you have some uncertainty there, then, this is within that uncertainty, disagreement. So, lots of different techniques are out there. How do you tell which one to use for your material, which, optical method you should use? Generally, you'd like to have some advanced knowledge about roughly the scale of the moduli of the material, the response of the material. That can help you choose the right technique if you have some idea about that. Basically, you want to make sure with your probe that you're in this continuum limit. Some people have said, well, I can't measure the displacements of the probes using my simple microscope and low-resolution CCD camera, so I'm going to introduce smaller probe particles because I can actually see those move around. Well, that may work for some materials, but the smaller you make the probe, you might have a problem because this continuum approximation might break down at some point. You have to have some idea or understanding of the characteristic length scales in the material in order to have some reassurance that this will work. And so basically, for this chart basically gives the maximum modulus that you could expect to measure with a variety of different techniques and the highest frequencies that you could go up to. Generally, low frequencies are not such an issue. And so for things like for methods like simple video particle tracking, you can go up to about 10 to the third dynes per centimeter square. You can do better than this with newer cameras that are out there, so you can go up to high-speed particle tracking. Basically here the modulus is limited by the resolution that you have in measuring the mean square displacement, so you have to be able to measure that mean square displacement to a greater resolution to get to higher moduli. And so you can do that with laser deflection, light streak tracking, diffusing ray spectroscopy. You can get up to higher moduli because those techniques can measure angstrom scale and nanometer scale resolutions of the displacements of the particles, typically. And if you want to go up to really high moduli, well, thermal energy with these probes is generally only going to get you so far, but you can apply much higher stresses with the forced excitations, like magnetic is especially good one. Optical is also good, but the magnetic I think holds the record for basically the forced microrheology in terms of the moduli you can measure. So biomicros, I'm going to get into more areas of current research interest now. So a lot of that was more or less review and summary. So biomicrorheology, it's beautiful. We want to understand the rheology of life itself, right? Okay, whatever, right? Sales words, but seriously, the cells are beautiful objects. They have amazingly complex dynamics going on. They have a cycle. They are stimulated by external and internal processes. And it would be wonderful to be able to understand more about the mechanical properties and the micromechanics, maybe active micromechanics in these systems, but thermal fluctuations aren't going to get you there. This is a beautiful field, but it's maddening, and people have been working in this area, even with beads and magnetic beads, I've told you, for decades, and we're using thermal approaches and thermal-driven approaches. Why is it hard to do? Well, it depends on all these things, the type and shape and age and how it's been handled and how you plated it and what are the molecular concentrations, your buffer strength, and and then finally you get down, probe interactions and transfection and all this, and then pretty soon way down here, there are the thermal fluctuations and your viscoelasticity and whatnot. So this is maybe not the primary concern, but I've been looking at particles moving in cells for over a decade, and I haven't published much on this at all because I want something to be reproducible and universal, and it's pretty hard to find that and do the experiments well with cells. People have a hard enough time with kind of reconstituted biopolymer solutions that they make from purified proteins or things like that. So that's hard enough, but I think we're getting there. Hopefully, I believe there's a way that we can learn more. I don't know exactly how much, but what we observe sometimes are trap escape cycles where you have a confined diffusion and then what looks like a limited convection plus diffusion. and then diffusion in a trap, and then convection plus diffusion, and you get these episodic dynamics, basically. So you can imagine a particle diffusing in dense, I mean, the cytoplasm is fairly dense, densely populated with molecules. Some of them are polymerized. Basically, you can imagine it in a network, you're scaffolding, and then it gets picked up by a motor, transported elsewhere, or the cell's molecular motors cause the entire scaffolding to change and deform, and it gets transported along, and then that process stops. So you have this intermittent dynamics. And if you try applying a thermal approach to that, you're going to get the answer all wrong, because you're not really, it's not diffusive motion, so you're not going to be able to extract the information. So we've done simulations, Daphne has done these nice simulations of trap convection episodic behavior, where you have trapping episodes and then convective episodes. And basically, if you just take these and blindly do the computations that we do for microrheology, make the mean square displacement up, look at the creep compliance from that, then what you find is you get something that looks like a diffusive slope out here at long times for these trajectories, but this is not diffusion, at least not thermal diffusion, right? And so if you analyze this data properly and segment the trajectories, so there's a nice problem in this of trying to take the trajectories and segment them properly so that you can get good statistical information about the trapping episodes and good statistical information about the convective plus diffusive episodes, and you might be able to extract reasonable quantities such as a velocity of convection or a distribution of velocities of convection, a strength of a trap, plus the potentially viscoelasticity. We'll see. I mean, it's not easy. So I have an undergrad REU student who's working on an inverse algorithm, which is basically taking experimental trajectories and then trying to figure out based on the slopes of the local mean square displacement. So you have a time series of the position of the particle, and you go in and probe that time series and expand out a window, and then extract the mean square displacement, look at the log slopes to see whether it's diffusive, subdiffusive, and based on expanding the window out, you try to determine different episodes of convection or trapping, and this is working. I mean, you can see there's some errors in this inverse routine, and he's right now defining the limits on this ill-posed problem to actually try to segment the trajectory so that we can extract average velocities, diffusion coefficients, and trap sizes. So that's an example of something going on in the yes, question.
Sorry, what is the data and what's the model?
This is model. This is data. Okay, that's actual data. That was in a mouse fibroblast. This is a model. This is a simulation, 2D simulation. Basically, we have a diffusion coefficient in water, and randomly we turn on convection and turn it off, or turn on trapping, turn it off, confine the particle to a certain radius, and then turn that off. And that generates trajectories that look like this. And and then in this case we have a simulated trajectory that was generated through a routine like the one I just described. And his program is taking the simulated trajectories without any information about the trajectory at all and trying to extract out the different episodes of behavior. And in general, that's an ill-posed problem. That's not a well-posed problem. And certainly as the velocity of the convection gets to be smaller and smaller, you would expect his routine is going to have some considerable difficulty to do this well. And so we're mapping out the limits of what we can actually do with this kind of an approach right now to see, it's not going to work for every condition, but it might be useful in some range of conditions. So I'm going to go on to lithographic colloids. So in microrheology, the probes are important, right? And having probes that are different shape might offer new opportunities. So it would be nice to have probes that are non-spherical. Like we had the wax microdisc that was made through if you would, a bottom-up process. And what about a top-down process for making shape-specific particles? So lithographic particles have been out since the early 90s. In fact, people made them before then, probably, and just threw them out. Threw out the baby with the bathwater, so to speak. In making MEM structures and other things, they probably had particles in their waste liquids but they didn't care to think about that as something useful. So, well, whatever. In any case, you can take the technology developed for computer circuitry and use it to mass produce lithographic particles. And this is a process that's a very simple one that we developed for doing this, in which we take a wafer, spin coat on a water-soluble sacrificial layer, and spin coat on a SU8 layer that's a photoresist layer. We can make a mask that has many replicates of the shape that we like, use a projection printing system to print these onto the wafer. The exposed resist is then developed. We wash away the unexposed areas that are not cross-linked. And our process basically uses an organic solvent to do that, so we don't dissolve the underlayer. And that enables us to develop for a long, long time to get very nice high-fidelity shapes. And so then we dissolve the underlayer and stabilize the particles, and we use a substrate. And I have a stepper in my lab at UCLA. It's the best lithography facility on campus, even though the electrical engineers don't like that so much. But, you know, I help them out from time to time. So anyways, this is a beautiful system. It's 350 nanometer feature size. I wish I had one that was 60 nanometer, but that's a little too expensive for me right now. So you could make these particles a lot smaller with such a system. But these are already fairly small, so the pen width here is a bit less than a micron. This is 3 microns right here, the scale bar here, the SEM images of particles. Here we've done the whole alphabet. We have toroidal donuts that are, well, these aren't really toroids, they're square donuts, frames if you would, plus signs, triangles, pentagons, you know, and the fidelity. I've been making particles for a long time. These finally have good fidelity. Okay, and the main reason is I tried doing contact printing, you know, and using a mask aligner all the time. And it's always just an awful thing to do because the particles all come out nasty looking in different parts of the wafer because you have dust or other things that eventually get on the mask. It's very hard to keep your contact mask clean, I've found. Yep, I'm getting there. So we also can put fluorescent dyes, and this was in the Museum of Modern Art in New York. These are particles made with that SU8, and in the SU8 we have different fluorescent dyes. We use Shimon Weiss's 3-color confocal microscope to take a confocal section of these particles. Basically, you can see we mixed 3 different dispersions with 3 different dyes together to get this image, and so this might be useful for marking or other applications. We can use the micro-defast alignment system on our stepper to actually align multiple layers, so we can print Janus particles that are Janus in the sense of shape, not just in the sense of material composition. And so this, I think, is a first demonstration of multi-layer types of particle construction with different dyes and so forth. We also do templating approaches, and we can mass produce particles by simply putting a sacrificial layer on the surface of a template, like on these pillars, and then coating that with a polymerizable layer or with something like gold, a solid layer through deposition, and then lifting off the particles off the pillars and reusing the template. So that's another way of doing it. There are multiple ways of doing this, but those are 2 nice ways. Basically, we have a variety of methods for doing this. I thought I'd tell you a little bit about trapping the particles, these dielectric particles. So we use a laser tweezer. We have to overcome the radiation pressure through basically gradient forces and torques. So we like these high-angle photons coming in. The low-angle ones don't do so much for us. And, well, we're going to tweeze these shapes, and these shapes are basically 4 microns by 7 microns, roughly a micron across. They're a little bit less. And we bring these in toward our single beam gradient trap, 1.4 Na. We're at about 17 milliwatts. Well, more than enough, much more than enough to trap spheres of roughly same size, you know. And so we know the spheres trap. Our trap is
Fine, we bring the particles in from underneath, radiation pressure begins to blow them up here, and then radiant forces take over, and we see if they trap. If they trap, we actually measure the position, and the arrow here indicates the direction of the average propagation of the light for that trapping state. And the green lines are just for symmetry. There's symmetry, reflection symmetry, or dots would be rotational symmetry. So here's the whole alphabet. So Jim Wilking deserves credit for this. Jim did a beautiful job on this experiment. Approached the letters at least 30 times for each letter into the track from different positions and orientations. And what he found is you could get very complex potential landscapes due to the interaction of pattern particles with a simple optical trap. And that's really pretty fantastic. So these letters, many of them have multiple trapping states, meaning that they'll trap, they have potential wells that are much deeper than thermal energy in several different positions and orientations, and you can access those by the initial conditions and how you bring the particle into the trap. You can reproducibly get to these states. And this is pretty interesting to have multiple trapping states. The end is something I'll come back to here. It traps here, but it has actually two preferred directions that can be accessed thermally. And there are interesting features like, you know, the I and the T trap like rods with the long axis along K, but L doesn't. And it has this long segment here. Look, J doesn't. It has a long segment there. U doesn't. So why does it prefer to trap out here on the side? And that has something to do with the torque. Okay, there are multiple trapping states. So here's, you know, why does the L trap this way? Well, basically, if it trapped this way, it would tend to slide up, and then this region right here would get in a region of strong field. You basically get an optical torque on this. So you have to remember the particles have to satisfy simultaneously both force and torque equilibria in the trap. And so we believe that a radiation torque makes this configuration fairly unstable, whereas this one, most of the higher dielectric constant material gets shoved out to the side where it's not interacting with the very brightest laser light that's there, the less intense light. I know I've only got a few minutes, right? You should wrap up. Okay. So
you have time for a few questions.
Sure, of course. We have done more than just letters. We've done systematic studies where we make toroidal frames and actually vary the size of the inner hole and trap them. And we find basically that we can shift the position of the trapping point. I should mention we measure this trapping point by bringing the particle down to the microscope slide, so it's not just our imagination. We actually measure these trapping points by looking at when the particle gets disturbed when it hits the microscope slide. So we go from moving this down then to changing this to look like more like a flagpole, and this is only transiently trapped for about a second. Here, if we make this interval bigger, then it becomes stably trapped again down in the corner. We thin it down more, we have another instability. So we have reentrant properties going on here with the trapping, and that depends on the geometry of the particles. Here's the end in the trap. This is what we see. Remember, we're looking at it from the bottom. All those other images are based on measurements that we made by dragging particles to the slide surface. But here you can see that the particle N is fluctuating between two preferred positions. And we can take a time series of the angle reduced from video, bin that out to get a probability distribution as a function of angle. So we see there are two preferred directions. And then we can simply use Boltzmann's law to deduce the potential as a function of angle. So we can begin to probe the potential landscape. And I think this is the first example of angular commerce hopping in a single trap that anyone's seen before. So I think this is kind of interesting. We've also done some nonlinear microrheology where we take a disk and we tweeze it. So this is in gelatin. And we apply an optical torque, and we basically go up on this curve like that, and then we remove the torque, just blocking the beam abruptly, and we get basically a creep recovery. And so that's a microscopic version of a step stress with a creep recovery experiment. And so we've done that, and basically we can fit the data fairly well and vary the laser power, and we wanted to see if we could go into the nonlinear regime and see if we could maybe see something like yielding in the material outside of the linear regime. We compare here basically the torque as a function of angle, which we get microscopically, with the stress as a function of strain, which we measure macroscopically, and we can overlay the data fairly well, and the geometrical constants that we have to do that scaling basically match up fairly well, meaning with we have to look at a volume swept out by the particle moving and rotating, and that seems to match up pretty well with our dimensions. So that basically wraps it up. Microrheology is a very interesting area. I'd love to see it expanded more into the realm of liquid crystals and anisotropic materials in general. I think there's a tremendous opportunity there for understanding viscous and elastic properties in very complex materials, actively driven materials. I wanted to thank NSF. Thanks.
We have time for a few questions. Can you just see where now?
So in doing the rotational diffusion microrheology, it seems that you are using optical trapping to hold the disk while you measure the angular fluctuation. It seems that your analysis assumes the thermal fluctuation. Am I correct?
Right, and so that's a good question. And so basically what we did is we had the laser power up high to align the disk so we could use the light stream tracking technique. Then we lowered the laser power down so that basically it didn't affect the fluctuations. So we still had plenty of photons to do the detection with, but we weren't exerting optical torques of any strength that mattered in the experiment. For a weaker material, maybe it might have mattered, but for this entanglement solution that we were looking at of PEO, basically it didn't matter. So we lowered the laser power, but we still had the light streak, so we could still use the optical lever. That was the trick that we wanted to play with and to get higher angular resolution. So our equation of motion did just have the thermal term, and it also had a very small optical torque, but that level was so much smaller than the other terms that it wasn't impacting our experiment.
I had a question on the same system, on the optical light streak measurements. Mm-hmm. You were using the trapping beam in order to get these light streaks, is that right?
That's correct.
And was it a visible trapping beam?
Yes, it was basically red Heaney light. It was, we thought about this, and it was kind of amazing because with circularly polarized light, we could get the disk just to rotate and spin, as you saw, and you look up above the microscope, and you have this kind of rotating light streak, on the ceiling going around, all from one microscopic disk that's trapped in a circularly polarized beam. We wanted to call it the discotheque, but that didn't quite go over, so we didn't do that. Question?
More questions? Time for one more. Would the next speaker come now? Who's the next speaker? Is the next speaker here? I saw there's a laptop there.
Yes.
One more question.
So, in those experiments, do you have to worry about local heating? Because, for example, if you use a visible laser, some of the materials would be absorbing a little bit, maybe some of the probe particles too. And if you heat some of the materials just a degree or so, properties may vary a little bit.
That's a very good question, Ivan. The answer is yes, you do have to worry about it, of course. For the techniques in which you're using a significant amount of laser light that might cause that local heating, you want to know something about the absorption of your probe particle. And typically, we want to work with low absorption particles, but there are cases where having high absorption might be. I'm going to get that just a sec. Where that might be useful for some imaging techniques, but maybe not for experiments involving laser illumination like that. Yeah.
very much. That was a wonderful overview. Okay, our second